All right. Uh, Today we are starting on chapter 22, but just a good review of what we learned in chapter 21 is that there is somebody had a question, all right, that when you have a charge of whatever Q in an electric and a magnetic field, then there's a force on this poor guy who has a charge Q. And the force on him or her is a vector sum of electric force, that's E, whatever is the electric field, and then the magnetic force. And the magnetic force is much more cunning because it captures you in a spiral. So this is now the name for this general expression is actually Lorentz force, but somehow the book doesn't want to give Lorentz any credit. But this is what we call the Lorentz force. It is a combination of whatever's your electric field plus this spiraling V cross B, and it depends on your velocity. If you were at rest, then and there's no electric field on you so that you didn't move at all, then you just say, quel le problème? You may have a strong magnetic field, but I'm at rest, then nothing will happen. But of course, in general, there's usually some electric field somewhere, and you are now moving, and because you're moving, you have a certain velocity, and you get trapped. So that is one concept. And the other concept is that when you are trapped in this spiral due to this external magnetic field B, and you have a certain velocity V, and your mass is M, then you will be going in a circle whose radius is this. And then the people who want to know more about you, they would actually put you through a certain magnetic field whose magnitude they already know. And they then see whether you curve to this side or to that side, because if you curve to one side, that means that your charge is positive. If you curve to the other side, then your charge is negative. And if you don't curve at all, of course, then your charge is zero. That's what they call gamma ray. That's the alpha ray, that's the beta ray, that's the gamma ray. And this is the radius of one of these, either alpha or beta. And you can know, if you know the velocity, you can then say, ooh, I can identify the mass of this guy, which is how they determined that it was the electron. But now the other thing, as we begin to go on in chapter 21, is that if you have a wire that carries a certain current I, and the wire is of length L, and it is now in the presence of an external magnetic field, there's a force on this wire. And the force on this wire, again, is a vector product. The mathematicians call it the vector product for the current in the wire, whichever direction is your wire. And then you have to now say it is I cross B times L. So that gives you then the direction of the force on this poor wire. I have a wire, and then somebody put a magnetic field, a strong magnetic field on my wire. Oh, then I find that, ooh, my wire is not going to be staying there. It is going to do something. There's a force on it. And then these are all sort of like in the presence of an external electric field, in the presence of an external magnetic field. But at some point, which is ampere, yes, at some point, the people who are studying this, making observations, making measurements, begin to ask, does the wire itself carry a magnetic field when it is carrying a current? When a wire itself has already its own current I due to your battery, when it itself is moving, namely the electrons inside, if there is already a current, will it produce magnetic field? Well, that's where they discover, oh, yes, and that's Ampere's law. And the magnitude of the magnetic field that is produced by your wire carrying a current I depends on this thing called permeability, mu sub 0, which again is a number in engineering units, divided by 2 pi r, such that if this is my current I, and this is my wire that has a current I don't have a wire right now, but anyway, if I have a wire carrying a current I, the magnetic field close to this wire would be strong. It's inverse, 1 over r. And the magnetic field that is far away from my wire, oh, it goes down like 1 over r. So this is actually Ampere's law, and the mathematicians have a more easier to understand than this, which is that the circuit integral of the magnetic field due to this wire that is parallel to the circuit itself, that the circuit integral of B dot dl is mu 0 I. Whatever is the I enclosed within that circuit. And if you were to apply Ampere's law to a circle around the wire, you get immediately this answer. Because for a given radius, the total circuit is 2 pi r. Then it is B, which is in the parallel to the circuit. B 2 pi r is mu 0 I. So that's how you get this. All right. So I just wanted to quickly review what we have learned in chapter 21. And now I got to announce. We had a test, right? Test number 1. That was supposed to be live. And it was live. Were you people alive last Wednesday? Did everybody show up? Yeah, right, I know. But you know, there's one thing that I could not understand. There were only about a third, 20-something, that in fact was present in MR3. And yet, when I opened the Blackboard exam, all 72 had their exams on it. I don't know how. If they're supposed to be live, and yet there's somebody, or there were more than 20, but certainly not 72. Certainly not 72. And yet the Blackboard shows 72. So and plus the fact that partly Blackboard, partly my own boo-boo, and which I confessed at the time, 4 of those questions had to be basically forgiven. So I actually spent time going over all the 72, and some people have double attempts, so I went through all of it and gave 40 points to everybody. Because I have no idea who was actually present last Wednesday, who was not present in MR3 last Wednesday. So I gave everybody 40 points. So whatever raw score you have, you can see it yourself. But just be aware that everybody got 40, right? Next time there's a test, I will ask the proctor to sign you in. Okay? Yeah, I did not, you see, because this is the first time we have this live test. I did not. It didn't occur to me. Now, is that another thing that I should confess? I think that's something I should confess. I was dumb and did not think ahead to indeed ask the proctor to have a sign-in sheet so that there will now be clear that, so so and so was there, and therefore only those people, their grades will count, and the rest of it I will just cancel. All right. So that is what I will do the next time around, and therefore this test one doesn't count. Call it a practice. Call it just getting acquainted with the silly fussiness and the quaintness of uh, Blackboard. Okay. Now what was this? So this exam does not count. It only helps you to practice so that you know next time, oh, the, you know, this thing about looking at the figures. And somehow when they click, some of you say when they click on the figure, it doesn't show up on the computer. I don't know. Those are technical issues having to do with your computer, which apparently was solved because one of you did manage to look and answer enough of the questions. So it is not that it is absolutely impossible. Many of those who were present indeed were able to look at the figures. All right. So there will be two more tests, and they will take over the three original tests. They will still overall the two tests coming will count as 45% of the final grade. Okay, the two tests, test two, test three, will count towards 45%. Test one is forgiven, is cancelled, is not count. Then the final will still count as 45%. And of course, the lab, the homework, they count as 10%. All right. Are you clear now on this policy? So the rest, the remaining two tests will count as 45%. Yes. Any questions? I can't see the chat so quickly. So,
I mean, what if we did well in the first exam? It just doesn't.
well, but given the circumstances, the fact that it was for some people the first time around, I cannot help on that. So right now, my
I
decision
mean,
is to just, yeah.
why don't you just drop the lowest grade? Because some people did well in exam one. You know, if they don't do well in the next exam, then it's kind of.
Yeah, no, but then some people complain to me and they say it's unfair because their computer didn't work the way it was supposed to, so they lost the time and therefore they were only able to answer, let's say, 10 of the 15. And so what should I do? So the fact that you did well, I say it's good. Therefore, you know that you are good,
Yeah,
comfortable.
well, yeah.
You will
So if
do
we,
very well in test two and you will do well in test three.
so you think that doing well in exam one is a good indicator for the next two?
What? What?
Doing well on the first exam is a good indicator for the next two, in your opinion?
That's right. That's right. Because
Okay.
you then begin to know the way in which I set up the test. And the fact that you did well means that you already kind of like your muscles are there. So it doesn't matter. The next test, ooh, you can do the dumbbell. You do this, you do that, you do everything. So that's good. All right.
All right. All right.
Okay. Any other questions or comments?
Professor, could you please add at least some points for our lab reports? Because it'll be really hard if your our exam, like the entire course get just based on like two exams. I mean, we're writing the lab reports every lab too.
Yeah. I mean, I
Yeah,
agree. I
no,
don't really see like why I'm putting in effort into the labs because it doesn't really count for my grade at all.
well, okay. Let me think about that because then it's just sort of like, fine tuning. What is this 45, 45, and 10? Fine tune it a little. So maybe I will fine tune, but let me think about that and think over it. Okay. Any other comments? Okay, so now let me just quickly go over the test, even though it doesn't count. The final will still be, I think, 45%, but as to whether the test 1, test 2, and the homework lab counts, that I have to figure out for myself, okay? And now let me just quickly go over the test. There was one question about why bits of paper are attracted to a charged glass rod. The correct answer is the paper becomes polarized, electrically polarized by induction, because of the induction. And then this one is one where you have two spheres that were already charged, and then you touch them. And well, anyway, it's you can download this and then you can read it yourself. I just wanted to show you the kind of answers that are the correct answers, and you know yourself what you did. And likewise with this, and this is one where you should recognize that when you have a positive charge here, the negative charge will be attracted to this side, but this originally had positive charge, so therefore there will be double the number of positive charge on the outside surface. That's why the electric field lines should be more. Okay, so anyway, so this is the, and then the thing about the train, you need to know the Doppler effect formula, and this is where I made the mistake. I somehow, in copying, because they were in the random block, I was copying, paste, copying, paste. Well, somehow this was left out when I pasted it. So this down, therefore, doesn't count. Missing question, so it doesn't count. And here is that thing about that involves permittivity of space, which is 10 to the minus 12. And I really hate Blackboard. When it is a number, so 10 to the minus 12, it just gives 0. Whereas when I entered in the number, it did have 10 to the minus 12. But somehow when it produced on your screen, it is 0. Why? Because it is 0.000000000000008. Well, so you see it as 0 and you say, what do I do? So it is now, from now on, when I need any number that is so small, I will make sure that when I enter it, it is in the 10 to the minus 12, and then it is numerically 8 or 8.5 or 8.4, so that there is no confusion. Somebody had a chat. I don't know what was the question. Who had a question? Somebody had a question? All right, so this is my not being acquainted with the quaintness of Blackboard, and so you are not, to be in any way punished for that. And likewise, because they were two calculated formulas and they both involve the permittivity. And then this one is just a matter of, what is the electric field due to these point charges, and you have to do the sum, the vector sum. And here is one where I did not realize that when this was written, I did not say W equal to a number and H equal to a number. And so you had no idea. And therefore, again, I had to discount it. But now I have, in my test pool, I have now added W equal to a number, H equal to a number, so that you know W refers to this and H refers to that. All right. Anyway, you can look at the PowerPoint. We need to get on with chapter 22, which is electromagnetic induction. And now it is very interesting because you see it all the time. We use it all the time. And in the field of science, it actually took a long time for the scientists, the physicists, engineers to figure out what ultimately we now know as induced EMF and the nature of that EMF, which is Faraday's law of induction, and so on. So we will come slowly to that. But here we just say, if I have a circuit and I didn't do anything, I connected it to an ammeter that shows the current that shows inside this circuit. I didn't move anything. There's no current. But if I now move this magnet, if I now move this magnet in, all right, now if I move the magnet in, the charges in my circuit, in my wire, right, they will now begin to feel a certain force. Oh, I didn't write down the formula for you, but there will then be a force that causes the charges in my wire to move. You remember that there is now a V cross B. What happens is when my magnetic field is now increasing, it is going to give a force on the conducting charges inside my wire to force them to move. And when they start moving, there is now a current. If I now first push it in, there's a current. When I pull it out, there's an opposite current. And so how you see that a changing magnetic field will induce a changing current. We will come later to figure out that this one is upward, this one is downward, but the first observation is that if I have a circuit like this, there's nothing that causes the charges inside my wire to move. But when I now shove in the magnet, so my magnetic field now is increasing inside, well then there is now a force on my charges inside the wire, and so they will now move. That is induction. So the main word that we kind of learn is that you can induce a current even though originally there was no current, and you induce a current by changing the magnetic field that goes through your loop. Okay, so the current in the coil is called the induced current because it is brought about by a changing magnetic field, and they call this EMF. They call this phenomenon, that the fact that you now are able to induce a current, they call that electromotive induction, right? Namely, I had no current, now I just stick in the magnet, namely the magnetic field now going through the coil has now increased. Ooh, there's now a electromotive EMF, and somehow the language came to be called electromotive force. And in a way, it is electromotive force, but what is now called EMF is not exactly force. I will sort of show you what is the sort of misnomer, right? But you can kind of sense that because of the fact that now my magnetic field is increasing, the charges inside my wire now react to that. And when they react to that, I get a current. So it is an induced current. And it is an electro motion because my electric current, they are now moving. So it is electromotive, but they call it EMF, electromotive force, although it is not really a force. All right. So for the moment, everybody just says EMF instead of saying it's electromotive force. And then you discover, oh, it's not exactly a force. So we just call it EMF, and we call this the induced EMF. Why? Because it was induced by my rapidly changing magnetic field. Okay. And this EMF can be induced by varying the area of the coil. X is represents the magnetic field pointing into the board, and the magnetic field are into the board, and this wire, even if you did not connect it to an ammeter so that it is no circuit there, but if you have this loop, there's no circuit to it, if you just vary the area of this, oh, then there is a EMF, even though it has not yet been connected to a, let's say, an ammeter or a lamp or some device that has a resistance so that no actual current is flowing, there's nonetheless an induced EMF. And we call it electromagnetic induction. All right. Are you roughly following the concept here? That you can induce with something which is electromotion, namely a current, if there were a complete circuit. You have now induced something which we now call EMF. There's a motional EMF that is induced EMF. So EMF is this electromotive, even though it is not exactly a force. And now let us take this case. I have a conducting rod. It is not what you call connected together. It's just a rod. All right, it's a conducting rod, but it is just a rod. It is not. There's no wire that connects this end to that end. If there's a wire connecting this end to that end, then there can be a current flowing in the loop. But no, for the moment, I just have a conducting rod. But now this conducting rod is moving in the direction V in the presence of an external magnetic field. And this external magnetic field is into the board. Now, each charge within the conductor is moving. They all are moving to the right. And then they will experience a magnetic force. You remember the formula? They will experience a magnetic force, which is Q, whatever is the charge, there's the plus charge here, minus charge here, Q V cross B. Now, V cross B, if you have your right hand rule, V cross B would be a force that would be which direction? V cross B would be a force that would cause the positive charges to be moving upward. You see it now? V cross B. Because Q is positive. Think of it as a current due to positive charges. I have V and I have B into the board. So I have V cross B, and V cross B would then cause my charges now to be moving in this direction. So I will have a current now. All right? You see now? It's due to the fact that now there is a force on the individual charges inside my rod. And the force of the individual charges is that now the positive charges are moving upward. And if they are moving upward, V cross B, because of the force, this now is a current. And if you were to have therefore connected it to a lamp, a bulb, the current will move. And the current will now be a continuing current so long as you are pushing it to the right. Are you following me on this? Okay. So the fact that you now have a EMF, electromotive force, but it's a misnomer. The fact that you have an EMF due to the motion of the rod, they call it the motional EMF. Uh, it is not emotional, it's just simply motional, meaning it is produced by the fact that your rod is moving. You are pushing. After all, the rod by itself would not move. But you were pushing. You see, there's this hand. You were pushing the rod. And because you were pushing the rod, you induce a motion of the charges inside this rod such that the current will now flow up. And then because it is completed as a circuit, you then find that there's a current flowing here due to the motion. So you call this motional EMF. Okay. Motional EMF, when V and B and L, namely the length of this rod, are mutually perpendicular. The book, if you look at the book, now if I ever I'm able to meet those guys in the Wiley Plus, I say, please don't use the E, because they didn't use a curly E. They use E that looks like electric field. They use E that looks like energy, but EMF is neither electric field nor energy. It is EMF. And so most of us, at least for me, I would not want to confuse, and I'll call it script E. All right, are you okay with my fussiness? If you were to look up Wiley Plus and look at the book, oh, everywhere it will have a ordinary capital E, like as if it is electric field, or like as it is the energy E. But no, it is the electromotive, and the electromotive EMF induced is VBL. And now there is a very interesting uh, thing that you can work on. Supposing the rod, they now say, well, you are able to push it and it is going at 5 meters per second, perpendicular to a magnetic field which is 0.8 Tesla. And that's quite strong magnetic field, certainly much stronger than the Earth's magnetic field. The rod has a length of 1.6 meters and a negligible electrical resistance. The rails also have a negligible electrical resistance, and the lamp has a resistance R. So now they say, and the lamp, the light bulb, has a resistance of 96 ohms. They say, find the EMF produced by the rod. Produced by the rod because I was pushing the rod. Okay, if I were to put this question, I would then say, find the EMF produced by the rod that is being pushed. Because if the rod is not pushed, there is no EMF. Okay, so now you say, all right, let me now remember that the engineers have figured out that when you have that EMF, the EMF depends on the velocity with which you are pushing it, or with which that it is moving, and the given magnetic field present outside it, and the length of the rod. So if you now say, okay, now you see, when I, you know, looked at the slide that they provide, they use this E, but this E is very easily confusing. So what I did was I superposed it with this script E. All right, this is the EMF according to the formula that the engineers have worked out for us. And if you now put it in, you say that this EMF is 5.0 meters per second, 0.80 Tesla, and the length is 1.6 meters. And by the time you work it all out, it is 6.4 volts. In other words, this EMF is not a force, because a force would have been measured in newtons. Instead, this EMF is a measure of the electric potential. That's why you call it volts. So EMF is not exactly Newtonian force due to the fact that you exert a certain force on this rod. Instead, it is simply the electric potential difference between this end of the rod and this end of the rod due to this motion V. So it is now, just to get a set of numbers, 6.4 volts. And you can now next ask, what is the current that now will flow? Due to your having induced the motion, by your giving this rod a motion V, you have induced a current. Now, what is the current that flows as a result of your having pushed it? Well, if this is the potential difference, electric potential difference, then the formula, the Ohm's law, is the potential difference is I times R. But now I am now more fussy, and I say, you better be careful. It is not electric field, it's not energy, it is EMF. Whatever is the EMF that now has been induced by your making the rod move with a certain velocity. And since we have worked it out to be 6.4 volts, then the current that flows is 6.4 volts divided by 96 ohms. And therefore you find, oh, the current is very small, 0.067 amps. All right. Are you following me on this? You should let me know if I'm going too fast. All right. Okay. All right. So now let us have this picture. Motional EMF, due to the fact that it is moving, and the reason why it is moving is because you have a hand pushing it. Okay. And now let us remember that when you have a wire that carries a certain current I and is moving in an external magnetic field, oh, there is now a force due to the magnetic field that is present. The force that my hand push is up to me. I want to go right, because I have nothing else to do. There are no exams, and I want to have fun, so I just push. Well, I push, but as I push, actually there is a force on the wire. There's a force on the wire due to the fact that there is a magnetic field, right? It's your magnetic field, whatever it is, so many Teslas. And now as I move, there's a wire, there's a current induced by me, by my motional EMF, right? I'm not emotional about it. I'm just having a lot of fun. And I am now doing a pushing this rod so that there is a motional EMF. But the very fact that there is now an induced current, the magnetic field that is present now says, haha, I will now exert a force on you. All you silly charges that are moving over here, that's the current. Oh, I will now exert a force on you, which is I L cross B. But if this is going upward, we have just figured that out by the motional EMF. If this is going upward, this current direction cross B is to the left. Are you following this? There is a force on this wire. The force on a wire due to this external magnetic field. The very fact that there is an external magnetic field, you are causing the rod to move this way. There is now therefore a current induced by this motion. But the very fact that there is now a current, there is now, it's like action and reaction. You know, Newton's law. There is now a reaction due to the fact that the magnetic field says, haha, you now have a current. I will now have a force on you, wire. Yes. And this force is, we already learned in chapter 21, is I L cross B. And I is upward cross the magnetic field into the board is to the left. All right. And now you can see, therefore, you exert a force by hand, the field exerts backward. And for you to keep this at that constant current, because you see, the current is flowing upward due to your motional EMF. And now you will have to do it yourself. You know, you have your own right hand, right? And now you have to stare at the screen and you say, I now have my 4 fingers point in the direction of the current. All right, do you see it? It is pointing in the direction of the current. And now I'm going to bend it into the direction of the magnetic field, which is into the board. And when you do it that way, your thumb is pointing left. Do you see it? Can you do it yourself at home? If you were live, then I can sort of at least show you, but now you have to look at the screen. All right, I have my hand, which is in the direction, my fingers, my 4 fingers, in the direction of the current that was induced by you, the current that was induced by this motional EMF. The current is flowing upward, but the magnetic field is into the board, so I got to bend it. I got to bend it like I am waving to you, beckoning to you, right? I got to bend it into the board. But when I'm able to bend it, my thumb is now pointing to the left. All right. So that is now the force on this wire, here, that carries a current I and of length L, and that force is to the left. You got it now? Have you tried it out at home? Okay. And so now you see what actually I was able to do is I push, I feel that there's a force, and I know that there is a certain amount of, 5 newtons or 10 newtons, and I'm pushing it steady so that this is going with a constant velocity. And I now say, haha, there's a current flowing. And we figured out in the previous slide that it was 0.067 amps, because the resistance was 96 ohms or something. All right. So you see now the relationship between motional EMF and electrical energy. That as a result of the fact that now you have an induced current, the induced current itself feels the presence of this external magnetic field. And so this wire now says, hey, there's a reaction. I was enjoying it, the fact that I get this, induced current, oh, those charges, they were so happy, now they can move, right? But the fact that they can now move, the external magnetic field says, you move, I'm going to, hit you. And that is this law, and that tells us it is the opposing it. Okay. In order to keep the rod moving at constant velocity, the force the hand exerts on the rod must balance the magnetic force on the current. Okay. Now, let's come to a very interesting application of this, because clearly, if I have to do this and I have to sit here and doing it, I will get tired, no? Well, maybe not if I'm very young, but I'm not that young anymore. I would say, forget it. But, oh, this one is another slide that says that the direction of the force in this figure is wrong. Because if the current is this way, I cross B would be F, but then my velocity, the one that caused it to go this way, is a hand here. So it is not balanced. What this says is, for this situation to hold, you are actually pushing and it does not work. Namely, it cannot be right. Are you following this, the point of this slide? That it does not work. It works this way, that as a result of your pushing, the force due to the external magnetic field on this wire is opposite. It cannot be like this. The force due to the external magnetic field on this, it would not work. And we will come to a very interesting application of this, which engineers are good at, inventing or playing. So I guess this could be a good toy that people can use. You say, supposing I have a conducting rod. I mean, anything that is made of steel or aluminum is a conducting rod, and I have vertical tracks such that this rod can slide down with no friction. All right. So if I have a two rails, vertical rails standing up, and I put a rod in between, if I have a rod that is here, of course it will fall. Right? Newton is always correct. You put a rod here and it is not bolted onto this rail, and you insert this rod into this rail, it will certainly fall due to gravity. But now they say, what if you have an external magnetic field? What if you have an external magnetic field? If you have an external magnetic field and this rod is now moving, will you induce motional EMF? Will you induce motional EMF? Yeah, you will induce motional EMF. And the motional EMF that you induce is, you remember, it is all the charges here, they are now moving with velocity v downward, and v cross b, b is out of the board, and now you are, if you are falling, so all the charges in the conducting rod, they are all moving with velocity downward. And if they are moving with velocity downward and B is out of the board, the force on these charges would be to the left. Therefore, the current would be flowing this way, which is what we showed down here. The current is now flowing this way. Do you see the picture? You are falling because of Sir Isaac Newton. Because of Newton, you are falling, and because you are falling, all the charges, conductors have charges. All the charges are moving with velocity v downward. But if it is moving downward, there is now a force on these charges, which is v cross b, and b is out of the board, out of the board. Therefore, the force is now to the left, and the current will now flow this direction. But once there is a current, due to the fact that you are falling, once there is a current this way, then this force law comes into effect. Why? Because the external magnetic field says, you have a current. Me, magnetic field, will now be able to have a force on you. It's like action, reaction. Now the magnetic field is reacting to it and say, hey, you have I moving this way and you have B out of the board. But I moving this way and B out of the board, the thumb gives the direction of the force. So the motional induced current, now there's a reaction to that due to this external magnetic field, and the force is upward. That's what this diagram shows. All right. And now you can say, see, this force and that force, they balance each other. They balance each other so that you have conservation of energy, and you can now work out. Oh, they didn't work it out, but you can work it out. There is now an upward force, and there was this motional EMF due to the fact that you are falling, and they balance each other so that I don't get tired, they don't get tired, and you can have this thing coming down very nicely, and you can control the rate, namely the force, by your external magnetic field, and you can control it so that if you increase the magnetic field or the force upward, and you change the acceleration of it so that you can balance it. Do you sort of get the picture? We leave the actual numbers out, but do you get the picture, right? The picture is that when you do it this way, it is so clean. Whatever is the velocity due to gravity, there is now a induced current. But the fact that you have an induced current, the magnetic field now says, I will now, force you. And the force on the current of length L is this much. And so you can have a balance. Okay, so now we want to come to magnetic flux. We have sort of learned about motional EMF due to the fact that the rod or whatever the circuit, due to the rod having some motion, it now has a induced current that follows. And we now want to introduce a concept associated with what is the magnetic flux. You remember from chapter, 20 or so? Electric flux. You remember Gauss' law? Do you remember? Electric flux? Yeah. Namely, what is the total, electric field always is perpendicular to the equipotential surface. And so You then want to know what is the net flux of electric field out of this surface. Well, here there's also this concept that we want to now introduce is magnetic flux. There is magnetic field coming out, whether it is due to a permanent magnet, whether it is due to an induced magnetic field due to your playing games with it inside with some kind of AC motor and so on. Whatever it is, you have produced magnetic field, and now you want to know what is the magnetic flux out of this volume, out of this surface. Well, we will now introduce this relationship between the electromotive EMF with the rate at which the flux, which we will define, changes. Okay, so now let's take this. You remember we had this example where this rod is being moved with a constant velocity, and this being going at constant velocity, you will know that at time t equal to 0, it was here. At time t equal to, I don't know how many seconds did they say? Well, this is a t0. At the later time, it is over here. This is what? Maybe 12 o'clock, 2 o'clock. So you know how far it has gone. X0. X0 is V times T0, right? And now you look at it later time. Instead of 2 o'clock, it's now 5 o'clock. So it started out here at 5 o'clock, it was over here. And now we like to know what is the electromotive EMF. And I quickly change that to a script E. It is the electromotive EMF. And the amount the engineers, the scientists have figured it out is V, whatever is the velocity, B, whatever is the magnetic field that you have, and the L is the length of this rod. But we know that this is moving with a certain velocity, which is, of course, x minus x0, where you were originally, where you are now, over t minus t0 times BL. Now, it is simple algebra. You can now write this as B and put the L in here, so that now it is XL minus X0L over T minus T0. But X times L, there is X times L is the area, right? X times L is the area. So that's A minus A0, the final area, initial area. And then you say, this is in fact BA minus BA0. Namely, this is whatever is the final flux. BA is what we call the magnetic flux. Whatever is the final flux through this area, surface, minus the initial flux. And this then gives you a law, namely that the EMF that is now produced due to your motion, you got nothing else to do, and you're just pushing it with constant velocity, then the EMF that's produced is the rate of change of the flux through this area. You notice it's sort of like now we're getting higher perspective. Instead of just like a nosy Parker and say, ooh, I got to now figure out what is the induced current, and then now let the engineers tell me the EMF is VBL, and then try to figure out all those interesting effects. But now we are getting higher and we are saying, yes, I know there is a electromotive EMF, whether it's motional, whether it is something else, which we will come to. So there is some induced electromotive EMF. And that now, we now connect it, we tie it with this concept of magnetic flux is the rate of change of magnetic flux. You can sense that this is sort of like Newton's laws. Newton's law was you have a force, and then there's a relationship between the force and the rate of change of velocity. Although actually Newton's law was not the rate of change of velocity, F equal to ma, but the actual Newton's law, when he formulated it, was the force, the net force, is the rate of change of momentum, mv. Here we are now saying if there is a electromotive EMF, that whatever is that EMF is related to the rate of change of the magnetic flux. Are you okay with that? It's sort of like going one step above. Instead of working with IL cross B, instead of working with the induced current EMF, VBL, we now begin to say whatever is the electromotive EMF, that is the rate of change of the flux, magnetic flux. Okay, are you okay with this derivation? I mean, this is a very simple derivation, but the most sophisticated one will come much, much later. Even in the history of science, the sophisticated derivation of this is something that required many years of figuring out. Are you okay with this concept now? That there is motional, not emotional, but motional electromotive EMF, and that amount of that EMF is related to the rate of change of the magnetic flux through your whatever circuit. This is now the circuit, the magnetic flux through the circuit, or the change of the rate of change of the magnetic flux. Oh, yes, and I have to immediately change it. All right. So this is therefore the magnetic flux through this coil, and the electromotive EMF that is induced is related to this. And so now that we have this concept of magnetic flux, we got to now be a little bit more sophisticated, or mathematically sophisticated. And if you have a surface, whatever area A, the magnetic flux is what the mathematicians call the scalar product, B dot A. There's a vector because the surface has an orientation, and you call this orientation A, vector A. Then magnetic flux is B dot A, or it is B times the area times cosine of this angle, because the component of magnetic field in the direction of the normal to the surface is B cosine phi, and the magnetic flux is B cosine phi times the area. So the magnetic flux is phi equal to BA cosine phi. Are you okay with this? I mean, this is a little bit of mathematics involved, just to be more precise, so that you're able to handle more general situations. Okay. All right. Okay. All right. So now, oops. If this is the coil and the magnetic field is perpendicular to it, it's just simply the area of the coil times whatever is the magnetic field. That's easy because basically phi is 0. The normal to this coil is upward in the direction of the magnetic field. So of course, it's just B times A, since cosine of 0 degrees is 1. But if it is a coil that is not perpendicular, but oriented this way, then the coil, the magnetic field, the perpendicular component is now cosine of 60 degrees, because this is the component of the magnetic field normal to this coil. All right. So if this is the orientation, then the magnetic flux is whatever is the magnetic field times the area of this coil times cosine of 60 degrees. And then, of course, what happens if my coil is exactly in the parallel to the direction of the magnetic field? Then the magnetic flux through the coil is 0. Why? Because there is no component of the magnetic field that is normal to the coil. So therefore, this coil doesn't feel any change in the magnetic flux, even as you change your magnetic field. You can change your magnetic field from 1 Tesla to 1500 Tesla, makes no difference to me. My coil says, what happened? Nothing. Because the magnetic flux is 0 and it remains 0. So then there is no electromotive induction. All right. So this is just to kind of get the concept of what is the magnetic flux, and we will be interested in the rate of change of the magnetic flux. Okay. All right. Now, graphical interpretation of magnetic flux. Well, this one is really, you have the magnetic lines, and this is your surface, and the magnetic lines now go through. So this is the surface that's perpendicular to this magnetic lines, and the magnetic flux is proportional to the number of field lines that pass through a surface. This is sort of like we did in chapter, I think, 20. You have electric field lines. And now you draw magnetic field lines, and if there is no magnetic material, whether it's ferromagnetic or diamagnetic, if you have no tiny magnets on the surface, then the magnetic lines will just go all the way through. But if there is some magnets inside here, they may have opposing magnetic field, such that the net magnetic field on this side may be different than the magnetic field on that side. But in general, the magnetic field lines on either side of this chip down here depends on what the chip is made of. Are you following my reasoning here? We should begin to recognize that each time you have a chip, let's say that this is not a mathematical surface, but actually this is a chip of some kind. The chip may itself have let's say a permanent magnet, a ferromagnetic material. And if the chip itself has ferromagnetic material, it produces magnetic field lines. And the net magnetic field line, this magnetic field line may oppose it or may not oppose it. And therefore, you have to now see the magnetic field lines on this side and the magnetic field lines on that side will not necessarily be the same. Okay, now we come to the central point of electromagnetic induction, and this is called Faraday's law. And for the Faraday's law, you are talking about a coil that has n loops. Oh, by the way, I should have, yeah. Yeah, I don't like this E, so I should have immediately. This is from the book. So this is now the electromotive induction due to a coil that has n loops, and the electromotive EMF induced, of course, depends on the number of loops, because each one contributes. And now we already learned that you can express that in terms of the rate of change of the magnetic flux through this loop, this coil of n loops. And the Faraday's law is that it is proportional to the number of loops, I mean the number of the coil with so many loops, and it is the rate of change of the magnetic flux through this loop, but there is a minus sign. The most critical aspect of Faraday's law is that there is a minus sign. Later, we'll learn something called the Lenz law, because it took them, all the engineers, all the scientists, it took them a long time to figure out this minus sign. And Lenz was one of the engineers that say, hey, it is always there to oppose. And so there's a minus sign. And it is the key feature of Faraday's law is that the EMF, the electromotive induced EMF, is opposite, is negative of whatever is the rate of change of your flux, magnetic flux. And the unit of induced EMF is volts. So that the actual Faraday's law is this Faraday's law. This becomes the fundamental law which you can use to figure out what is the EMF if you know the rate of change of your magnetic flux. It makes the calculation much faster. Instead of having to figure out, oh, there's this EMF induced current, and then you have to then reassociate it with E equal to VBL and so on. That all you have to do is to say, what is the rate of change of my magnetics through this coil, of which there are n loops, and then the EMF that is induced is opposite, negative. All right, so basically, this is really, after the concepts involving induced EMF, motional EMF, after those concepts, the key formula in this whole chapter is this formula. Faraday's law of electromagnetic induction, that the amount of electromotive induced EMF is proportional to the number of loops times the rate of change of the magnetic flux through your coil. And now it's my custom to now say, sit back and say, who was this Faraday? After all, as I keep emphasizing, this whole chapter in the history of the study of electromagnetic induction is Faraday, and this law is not named after Faraday because volt already is the concept language. So it's called volts, although Faraday was honored with the name for the capacitance, right? So many farads. Well, here is the picture of Michael Faraday in the 18th century. You notice that this is much later than Newton. Newton was 1600 something. So this is much later. And I looked up the Wikipedia for Faraday. And I just want to spend a little time to encourage you. You know why? Faraday was an excellent experimentalist. He was not a mathematician, not like Friedrich Gauss, not like Ampere, Christian Ampere, right? Ampere. So, but he was an excellent experimentalist who conveyed his ideas in clear and simple language. He was really an engineer, and more than an engineer, he's also a chemist. But the one thing that you may want to sort of be interested in, his mathematical abilities, however, did not extend as far as trigonometry. And they were limited to the simplest algebra. Isn't it surprising that you have someone so famous in the whole field of electromagnetic EMF, in the study of electromagnetism, that this key person, yeah, I mean, you can say, how is that possible? Because you see, he's good with his hands, and he did a lot of experiments, and he was just able to say, there must be a simple way to explain this. And so he came up with more or less the way we did it. We say the EMF is, proportional to the rate of change of the magnetic flux. He was able to kind of go up into this magnetic flux concept. Now, in the history of science, in the history of physics, the importance of Faraday's law was made into the highest mathematics, not at the level of trigonometry and algebra, to the highest by James Clerk Maxwell, a British scientist. Well, Faraday is also British. James Clerk Maxwell, who later, I forgot, but it's closer to the end of 1800, took the work of Faraday and others and summarized it in a set of equations which today is the basis of all modern theories of electromagnetic phenomena. It is incorporated, Faraday's law is incorporated in what is called Maxwell's equations. You will not be involved with the study of Maxwell's equations, but for any physics course, like 207, 208, they will need to learn something about Maxwell's equations. And for Maxwell's equations, you need to have calculus. So, but anyway, this is just to kind of like point out that you can be a, let's say, inventor, not inventor, you can be coming up with new observations, key observations of new laws of nature, of new laws of biomedical application, because you are able to see what is new, because you already know the basic concepts. You did something in your lab or in your clinic somewhere, and then you say, woo, there seems to be a new, law involved. There's a new phenomenon involved. And then you do a lot of tests here and tests there. And Faraday spent a lot of time doing all these engineering aspects. And that's how he, in the end, figured out this Faraday's law. Okay. And now the other part is Faraday was not just a engineer, experimentalist. He was more a chemist. So he discovered benzene. I guess, do you know what is a benzene, right? He discovered what investigated the, I have no idea, clathrate hydrate of chlorine. I'm not a chemist. Some of you have taken chemistry, so you know maybe what's a chlorine. And then We all learn what is Bunsen burner. I didn't realize it took Faraday to invent a Bunsen burner. I guess, yeah, it does take some genius to be able to invent that. Such that all you do is you turn something and there is the fire that comes out. And the system of oxidation numbers. But the other thing that is attributed to him is he invented the name terminology of anode, cathode. Do you know what's a cathode? What's an anode? Did anybody, do you know what's a cathode? What's an anode? Anybody? What's a cathode? Yes, I know. But what is it? Is it positive or negative? A cathode. Negative. Thank you. An anode is positive. Yeah. It's important to know that because when you have all these batteries, the side which is flat is the cathode, and the side that is sticking up is the anode. And when you connect a series of batteries, you better make sure that it is in series, so that you can build up the charge. And electrode and iron, but anyway, this is now we have. Okay, so now let us make practical use of Faraday's law. So we now say, I have a coil. I have a coil of wire. Oh, wait. I have a coil of wire consists of 20 turns. That means that N is 20, which has an area of 0.0015 meters squared. So that means that it is a coil that has not such a big area. Okay. I guess when I put up this kind of questions on Blackboard, I better not write it as tell it that is 0.0015. I will have to tell you it is what? 15 centimeters squared. All right, I have to tell you it's 15 centimeters squared, and then you work it out as 0.0015. Because if I tell it 0.0015, when you have it on your test, it will say 0. It may not show you 0.0015. But anyway, this is what I have learned as a lesson from test 1. So you have an area of 15 centimeters squared. A magnetic field is perpendicular to the surface. That makes it easier for you. Initially, the magnitude of the magnetic field is 0.05 Tesla. And 0.1 second later, it is increased to 0.06 Tesla. So the magnetic field is changing. Therefore, the magnetic flux is changing. And now they want to say, what is the average EMF induced in this coil during this time? So this is a very simple, direct application of this Faraday's law, right? From now on, we'll call this the Faraday's law. The sophisticated version, we'll leave it to Maxwell. So this is the Faraday's law, and the book, I hate them. They write this as E, but I quickly have to change that to curly E. EMF is negative N delta phi delta T. So therefore that's minus N, minus having to do with the way in which the induced current flows. And it is now BA cosine phi minus B0 A cosine phi, namely the final magnetic field and the initial magnetic field. Well, that just by algebra is minus NA cosine phi B minus B0 over delta T. And so you are told it is 20, you know, the coil is 20 turns and the area is 15 centimeters squared and it is perpendicular to the surface, so it's cosine of 0. And this is the change in the magnetic field, zero point 0, final, initial, 0.05 Tesla in zero point 0.1 seconds. Therefore, when you work it all out, this one is induced EMF is millivolts. That's because your rate of change of the magnetic flux is not so big. If your rate of change of magnetic flux is big and you have a lot more coils in, or you can make this EMF big. And in technology, in engineering, they now don't just simply have 20 turns. I have no idea. It must be a few hundred or even 1,000 turns, right? And what they want now to do is to have a big EMF. Well, what happens is they now make the magnetic field, the change, big, fast, and you will then have a big voltage. In other words, you can now use this in many applications. And later on, there's a generator. When you have a generator, you are now having a coil that is now turning. And when you now have a coil that is turning, there will then be a change in your magnetic flux due to the fact that the coil is turning. And you can now arrange for it so that it will now produce a current at a high voltage because you are able to change the magnetic flux. You are able to make it go turn faster and faster and faster. For the uh, Con Edison, they have made sure that the rate at which it turns is at 60 cycles per second. That's the hertz. Whereas in other countries, they go at 50 hertz. And they then later, we will learn how to, when they produce it, the EMF, the voltage is, I don't know, let's say 200 volts or 300 volts or 400 volts. And then they use something which we will learn later called transformer that can step it up from, let's say, 500 volts to 300 or 675,000 volts. And that's all for economic reason, because if you are able to step up the voltage by transformer, making use of this induced EMF, if you are able to transform it up to 675,000 volts, then the current that flows now is smaller because the power is I times V. And if you have made the V big because you're able to step it up by a transformer, then the I will be small, and therefore the heat loss, I squared R, the heat loss in transmitting it from Niagara Falls to New York City will be small. And therefore, the power, so many megawatts that they have produced, they will still have so many megawatts. Maybe it's 1% less or 0.1% less, but there's still enough for them to charge you for your use. And then over on this side, they will step it down, step it down, step it down to whatever is the household, which in America is 110 volts. Okay, so this is just the first simplest application of Faraday's law. Any questions? Okay, no questions. All right, so now this is a fun. question. I don't know if you do you know what is an induction stove? Has anybody do you have an induction stove in your home? Or do you have the old fashioned? Huh? Yeah, you don't have, right? It's only the modern kitchen will have because you need an electrician to set it up. But have you seen this? It is a very special. Yeah, so you have seen this, but you may not have it in your kitchen, right? It's a very special stove. You have no Bunsen burner. You don't turn on anything by the old-fashioned, match, right? You want to say, hey, I want to light a fire and I'm on a campground and I'm outside. There's no way to have a induction stove. There's no way to have a Bunsen burner. So you use your matchstick. But here, you don't have any matchstick. You don't have anything. All you have is a sort of a surface, a board. Of course, this is a very special board. The engineers, they tell you, oh, they have to design this and they have to have a certain thickness and so on. But we leave it to the engineers. All we want to know is, what is the principle? What's the concept that you're using? So they say, I have 2 pots of water. They are placed on an induction stove at the same time, right? So on the right-hand side, I have this pot, and the left-hand side, I have this another pot. But this pot is a glass pot. But this one is a metal pot. And then you will then immediately say, ha ha ha, I kind of know. If you have a metal pot, then there's somehow something to do with electromagnetic induction, right? This glass is not a conductor. There is no way in which there will be any current due to whatever magnetic field you produce, right? So this side, you turn on, because there's a switch somewhere, you turn on, this guy doesn't boil. But this guy, after a while, the water in the ferromagnetic is boiling while that in the glass pot is not. How can such a cool stove boil water, and why isn't the water in the glass pot boiling? Right? It's a very interesting question. And so I downloaded a picture. I downloaded a picture of what actually is underneath this induction stove. And the surface is a ceramic surface and of a certain thickness. The engineers, they have, after many trials and errors, they have settled on this kind of ceramic, and it has to be, a certain thickness, because if the thickness is not right, then there's not much of a induction that can flow through, because you want the magnetic field to come through. You remember what I said? If this surface itself has some magnetic, material in it, diamagnetic, paramagnetic, ferromagnetic, then it interferes with the magnetic field that is now due to this induction. So what happens is you now turn on, and the coil is supplied with high frequency alternating current, that you get from your power supply. And this rapidly changing magnetic field, because the current is now flowing, there is now a magnetic field that is produced due to the current that is flowing. And there is a change in the magnetic flux. Why? Because this is an AC current. Do you see what I mean by AC current? The current that comes from Con Edison, it is alternating current. So it's 60 it's 50 hertz, 60 hertz. So every fraction of a second, it's flowing this way and then that way, flowing this way and then that way, this way and then that way. Therefore, the magnetic flux through this coil is now changing at a high rate. You remember it is delta phi over delta t, right? And as a result, now there's a magnetic field that is now go through the ceramic surface, and now these are themselves metal, ferromagnetic. They are metallic. And when your magnetic field, due to underneath, somebody is the Con Edison, the current is flowing, so it has changing magnetic field. Therefore, the magnetic flux through this coil, because after all, this is a coil, it's made of metal, so it is a coil. Therefore, the magnetic flux through this coil is changing. If this magnetic flux through this coil is changing, then Faraday says, aha, there is now an induced electromagnetic induction, EMF. And this EMF will cause these charges on this pot to be now jiggling around. And when they are jiggling around, they are knocking each other, they produce heat. They are knocking around each other, they produce heat. And it is this heat that boils the water. I mean, I'm giving a very simplified overview of what is this induction stove. But this induction stove is now, many kitchens, they have it. Okay? Do you kind of at least get the concept? Leave it to the engineers to figure out what kind of material and the number of coils they have in there underneath. I don't have any idea whether it is 10 coils or 50 coils or whatever. That the engineers, they have learned how to do it. Okay, so now before we now end with lens. That's that minus sign. It took the people in this field a long time to figure out how to figure out that there is a minus sign. The induced EMF resulting from a changing magnetic flux has a polarity that is opposite to the original, to the actual flux change. All right, there is this minus sign, and it was Lenz who then says, hey fellows, whoops, hey fellows, I have to put my wire in. All right, it is Lenz who says, hey fellows, the way you handle this is, okay, so now there's a reasoning, there's a way to think it through. He says, okay, first, determine whether the magnetic flux that penetrates the coil is increasing or decreasing, namely delta phi, delta t, the rate of change of magnetic flux, whether it's increasing or decreasing. Well, that's just to get the rate of change. Find what the direction of the induced magnetic field must be so that it opposes the change in flux by adding or subtracting from the original field. In other words, you have induced a current. It produces a magnetic field. But originally, I already have a magnetic field. Are you following? Originally, I already had a magnetic field. And now, because of this electromagnetic induction, there is now a current that flows, which produces its own magnetic field. And now this magnetic field that is produced by the induced current must be to oppose your original magnetic field. You understand? In other words, there was this magnetic field. And now, because you were so smart, you were able to induce somehow, and we will come back to this, somehow you induce this electromagnetic induction. So now there's a current that flows. But Lenz says the current that actually flows is so as to oppose whatever is your magnetic field coming through. Because you woke me up. You woke me up so that now I have a current, induced current. But which way, when you wake me up, which way do I run? I will run, namely the current, so as to oppose the magnetic field that caused me to wake up. Like I want to sleep, but now you suddenly woke me up, and what I want to do is to shut off the alarm. I don't want to go back to sleep. Well, in that way, this Lenz's law is saying when you have a original magnetic field and it had an UMF induced, that the induced current will be one so as to produce a magnetic field that opposes the original one. And that is Lenz's law. Well, we'll come back to this the next time, but it's now 6:40. All right. I will now end the recording. But if you have questions,